I'm gonna go pause my laundry.
Okay, should be recording now, so we got about 6 minutes here.
I'm gonna tell him to be quiet, but I apologize in advance if my partner comes in and says hello.
Okay.
He's making dinner, so I can't complain.
Informal.
What?
It's gonna be pretty informal.
Sounds good.
You got a message on the screen here. No.
Yeah, meeting is being recorded. Okay. Got it.
Well, thank you so much. I was the first one here. That's why.
People that haven't been here before need to know where the bathrooms are.
Thank you, Anne. Thank you, Anne.
Hey guys, anybody not been here before?
Uh-huh.
Have you been here before?
Years ago during piano
Okay.
recitals and so forth.
Yeah, there is a restroom if you go back here and turn
Yeah,
right.
she showed me it.
Yeah.
Did you hear about the pink sofa in the living room?
The pink sofa.
Pink sofa is in the paper there last week.
Oh,
They're
no.
going to restore it, but it looks beautiful where it is.
Yeah.
Katie necklace.
Has anybody not seen the meeting place where we're at right now?
Necklaces.
Has anybody not seen it?
Not seen what?
Where we are here right now? Can you guys see me here? We're in the library of the Butterworth Center here in
Alex just said
Moline.
hi to you.
Oh,
She's typing. She's messaging.
And I don't know if I can show you this here. Yeah, there's Ann waving. Here's the room that we're in. It's a fairly good sized room. You can see
Ceiling.
the ceiling is really nice.
Oh.
There's a very large, what do you call it, a mural, I guess, on the ceiling.
Oh, that's beautiful.
And that came from Italy, I believe. The Butterworth family entertained a lot of people. You know, the Butterworths were John Deere people, basically. And they built this mansion here to, host meetings, company events and things like that. And so we now have the opportunity to use it for our astronomy club meetings. So we got about maybe 2 minutes here. I'm going to switch over to sharing my screen here. If I can figure out how to do that.
I invited Katie's next door neighbor to join us tonight. Her name is Nancy Bergman. So you might see her name.
Oh, that's so sweet.
Hey, I know her.
Oh, you do?
Yeah, I heard it from my mom, Chris.
Oh, that's awesome.
Yeah.
Yeah, they're very sweet. We're good friends.
Yeah, she's known you since you were 3 years old, she said.
Yeah, we've come a long way. She still does me favors whenever I need something from Iowa. She comes out to Colorado quite a bit, so she'll drop me off something from my parents or every now and then.
Beautiful.
So my computer here shows that we have 18 participants on the Zoom meeting, and we have about 9 people here in the room. So that's a pretty good set of people. We'll wait just maybe one more minute in case there's some last minute people wanting to get on, and I'll monitor here while we begin our talk. I guess maybe before we start, are there anybody here that are visitors that would like to maybe introduce themselves? I can hang on a second. Before you do that, let me unshare this here. I think it might be good. Okay. Is there anybody new here? You want to introduce yourself?
Sure, my name's John Davis, live in East Moline. Wife, 2 kids. Pretty much it.
Interested in astronomy. This is a popular astronomy club meeting. I assume you're.
Oh, it is? Oh.
Sounds
I
like he,
thought this was the Better Business Bureau. I took a semester at Tybor Community College. After I left the Navy, got my business degree. Just always been a sort of a hobby fan of astronomy and getting my kids into it.
Good.
So didn't know there was a club here. So yeah, there's a club.
Did you sign our register there?
Yes,
John
sir.
did more than sign. He joined.
Oh, good, great.
Our newest member.
Next time bring your kids.
When you're on a ship, is there a lot of observing of the sky? When you're on these ships out in the ocean there?
I to tell the truth, I didn't do a whole lot of that. I worked in the bowels of the ship in the engine room, so what time I did have, I didn't really. I can tell you when we were out to sea, it was dark. When you were out in the middle of nowhere, you know, God bless you if you fall off the ship, because no one's gonna follow. And I was on an aircraft carrier, so yeah, the people working on the flight deck, they have colored life vests and then these little dye things that if you get blown off by a jet engine, it's supposed to light up when it hits the water so that they find it. But I would imagine you could see a lot, given there was no light pollution at all.
Yep.
You know, that's probably even in East Moline, there's quite a bit of that. So
Yep.
when you get those moments, see the whole sky, that's cool.
And welcome to our meeting, and thanks for joining. And we have another visitor here.
I'm Colette Erickson, and I am just interested in the skies and have been for quite a long time. But at my age now, I can't go to Niobe to view out what I'd love to do, but it's hard for me to drive at night. So I just decided to come. I called Mr. Scheidler about something I saw in the sky several months ago, and he confirmed what I didn't know. And so it was interesting to me, it always has been, but I know now that there's so much more to the skies and to the heavens that I'll never be able to remember and grab a hold of it. But it's interesting to come here and see what I can find. He told me Venus was out there tonight by the moon, so now I know the third planet that I have. Nice to be here.
Thank you. Is there anybody online that wants to introduce themselves before we start? It's okay if you don't, but
I think it looks like Allie might. I think she was nodding her head, right, Allie?
Yes.
I haven't met you yet either. Hi.
Oh, good. Hi. So my name is Allie Nordic. I'm a RISE student. I'm a Road to Independent Spatial Employment student. I'm at Georgetown University, and this is I'm a first year RISE student, so I'm a freshman. I'm in Alton, Illinois. I live in Western Illinois. With my parents, names are Gary Nordic and Chris Nordic. And here at Jefferson, I'm just totally blessed to be a part of it. And so sometimes now from the daylight saving time that had ended, and I'm just so thankful that I know about bands and so on. I know and band too. So when I'm looking at the night sky when I'm on campus, I get to see star, a planet, the moon, and this, for me, like, hey, I'm thankful for that because when I know that, it's related to astronomy. So I've been that. So this for me, I'm just thankful for me to be part of the RISE program. So I'm a RISE program student. I have Down syndrome, and I'm doing well.
Thank you.
So nice to meet you, Allie. And this is another unfamiliar face. This is my boyfriend, Jacob. He's also an astronomy nerd. We met at AAS in 2019, and now he lives in Colorado too.
Cool.
So anyway.
Hey, Jacob. Glad you could join us, Jacob.
Oh, I'm glad I could join too. Katie actually started talking about this club the night that I first met her 2 years ago.
I'm a big fan.
Yeah. So I'm happy to be here. I'm happy that you're getting to present too.
Who's gonna hang out over there?
Yeah.
Yeah, and he chose a good vocation to pursue.
For sure. I'd say we're a little biased though. Anyway. All right. Thanks, guys.
Okay, so on the agenda here tonight, I guess we did our welcoming. And I guess the next thing is our speaker tonight. If it's okay, Katie, are you ready to go? I'll introduce you here briefly if you're ready to go.
I'm ready whenever.
Okay, so Katie Melbourne is actually a member of our club and has been a member for, I don't know how many years, but quite a few years. So you're from the Quad Cities. You're a systems engineer now at Ball Aerospace. And also you're a PhD student in aeronautical engineering at the University of Colorado Boulder. And you also have degrees from Yale University, and I don't know what all other degrees you might have, but you worked at NASA and you're highly qualified. So I guess with that, your presentation title, if I'm correct here, is Liftoff, the James Webb Space Telescope and its journey to launch.
That's right, Professor Al.
All right, Professor.
Not there yet, but maybe someday. I will go ahead and share my screen. Well, I think I have to share before I go into presenter mode. Hang on. I feel like there's always a second here of desktop one is this one. Oh my goodness, hang on. I didn't realize that I have to log in and say, yes, I can share my screen from Zoom. Okay.
No pressure here.
Hang on 2 seconds.
Is she allowed to share? Oop.
Captain Butterworth.
She might have to come back on again.
She said she didn't want to come back.
Yeah, here she is. I gotta read it in her again. This technology is kind of clunky, I think.
Oh, that's Roberta.
Okay, can everyone hear me now? I think I should be able to share my screen. I changed my permissions.
Okay, good.
Sweet. Now can you see my internet right now?
Yeah, we see the launch meeting screen.
All right.
Go for it. And
Present to
everybody-
view.
before you start, everybody, if you would mute your microphones until the end, and then we'll take questions at the end. But if you mute, then it'll be more quiet so that we can hear better. So take it away.
Awesome. Thank you. And if anyone has questions, I'll try to monitor the chat. So if anyone online wants to message, just let me know. All right. So thanks, Al. So yeah, as Al mentioned, I now work at Ball Aerospace, which if you've ever seen like the mason jars, we used to make those. And then one of the brothers was really interested in aerospace, and they figured being around the University of Colorado Boulder, they might as well start an aerospace branch back in the 50s. So I work in Boulder, Colorado, but we also have a couple of other locations throughout Colorado. But the bulk of our spacecraft work is here. And so at Ball, we build and design spacecraft, sometimes for space missions, other times for Earth science missions. And sometimes we design and build the entire spacecraft. Other times we just build certain payloads or instruments that ride aboard other spacecrafts. So we'll contract with other companies and NASA for that. But today we're going to talk about NASA's monumental space exploration mission, the James Webb Space Telescope, which I'm really lucky to work for. And I realize that I'm sharing the chat on the screen. So I'm going to move that so you can see the Space Telescope in all its glory. Okay, there you go. That's James Webb. And I've worked on the program for about a year now. And luckily, we are now 39 days from launch. So I slid in right before launch. And I'm really excited to share with you what it's going to be all about. So as many of you probably have heard of, right now there is a mission that's been going on for about 30 years, the Hubble Space Telescope. So right now it's the most famous telescope and most probably the most beloved telescope in the world. And Hubble was launched in 1990. And it just so happens that the 5 instruments it now carries are all designed and built by Ball. So we have had a role in these large space missions for quite some time. And Hubble is traveling in a low Earth orbit about 350 miles above us, and it's traveling over 16,000 miles per hour. It's all still operating, but it's getting up there in years. It's over 30 years old. And so all the beautiful images of planets, galaxies, and stars we've seen, most of them are captured by Hubble, and it's been used for thousands and thousands of observing campaigns. And here are a few of those wonderful pictures. Hubble's done a lot more than just give us incredible images. It's led us to innumerable major discoveries in both astronomy and astrophysics. And that includes how stars are how stars are much more varied and complex than we ever knew, how they develop in huge clouds of gas and dust, how galaxies interact and merge, as we see in the center bottom image here, the long tails of stars and gas. And more importantly, Hubble has helped us understand how the universe was formed and evolved. And I actually have talked to you guys before at a previous presentation about some of the work that I used Hubble data for, which is my work with M-Dwarf stars. So Hubble is near and dear to my heart, but it's exciting to get to work on the next thing. So back to the expanding universe question. It was astronomer Edwin Hubble, Hubble's namesake, who found nearly all the galaxies are moving far, far away from us and far away from each other because the universe is expanding. There's a famous analogy that helps us understand this concept. So imagine a lump of raisin bread dough, and the raisins represent galaxies in the universe. As the dough rises, the raisins move further apart, but they're all still stuck in the same dough. Hubble observed that a galaxy's spectrum, the range of light waves it emits, redshifted as it moved farther away. In other words, its wavelengths got longer and longer, and the light is shifted to the red end of the spectrum. Now, he was the first to tie in the redshift phenomenon to an expanding universe. And so on the left here, we see Hubble observing from the Mount Wilson Observatory in Los Angeles, whose data I have also used for my astronomy research. And right here on is Hubble Space Telescope's image of the galaxy cluster ACOS 295. And you can see many background galaxies and stars in this picture as well. So a little bit more about redshifted light. The longest visible wavelength to humans is red. So beyond red, there are longer wavelengths we can't see, starting with infrared. When light is stretched and expanded, stretched with the expansion of space, we say that it's redshifted from its original wavelength to a longer, redder one. The greater the redshift, the greater the distance the light has traveled from us. Thus, infrared telescopes are needed to see light from the first, very most distant galaxies. So, like all telescopes, Hubble and Webb are both time machines. Light travels very fast, 186,000 miles per second, but it still has to move across the vast distances of space. The greater the distances, the greater the time difference. So light from the sun needs about 8 minutes to reach the Earth, which is about 93,000 miles away from the sun. But light from the next nearest star needs 4 years to reach us from across space. We say that star is then 4 light years away. The light we see from that star in today's sky is also 4 years old. For galaxies, we're talking millions to billions of light years. So we see the furthest galaxies as they appear in the early universe. The light that left them way back then is finally reaching us now, which is why we call this a time machine in a way. Hubble has seen light dating to about 400 million years after the Big Bang, light that took about 13.3 billion years to reach us. But with Webb, we'll be able to look even further back than that. It should take us to about 250 million years after the Big Bang, which may not sound like a big difference, but it is in terms of seeing the earliest light. So we need a bigger telescope. I really like this image because it gives you just a sense of the scale of the mirrors, and got my little model of it, and it does nothing in comparison. But to see further, fainter objects, we need a bigger telescope. In particular, we need a bigger mirror because mirror size is the most important feature that makes a telescope powerful. The bigger the mirror, the bigger the area to collect light. And Webb's primary mirror can be much, much larger because it's actually 18 different mirror segments. They all work together as one. So Webb's resolution will be about 100 times more powerful than Hubble's. And JWST could probably see a bumblebee on the moon, is what John Mather, our Nobel laureate and lead project scientist, likes to say, which is pretty cool. And it's a big one. So this isn't the real telescope because that would be a nightmare for our clean room people, but it's a full-size model of it. And this is a bunch of Goddard staff, NASA Goddard Space Flight Center staff that worked on Webb, standing in front of the model of it on Goddard Space Flight's campus. And it's a funny looking telescope, isn't it? So you see these big honeycomb thing features standing up. That's the main primary mirror. And then the big stretched out layer below that looks like a kite is the sunshade. And that's exactly what it does. It shades the mirror from the sun. And the sun would just make the telescope too hot. So this is a very necessary part of the design. And the sunshade shade is huge. You've all seen a tennis court. That's the size of this piece right here in the gray. So here's a drawing of the Space Telescope in all its glory again. You can see the sun in the bottom left corner, and that ball near it is Earth, and there's the moon just beyond that. And Webb will eventually go way past our moon, about 1 million miles away from Earth. So it's non-serviceable is another big thing, big difference from Hubble. So, like I mentioned earlier, infrared is a very special type of wavelength that will allow us to see way back into time in our universe. So there are many different types of light waves, but our eyes can only see visible light. And Webb needs to observe an infrared because that's the wavelength of light emitted by the furthest objects in the universe. So with an infrared telescope, we can see through dust, sense the temperature of objects, search for cool and dark objects, and see really distant galaxies. And these photos show exactly what I mean. In the left here, we see the constellation called Orion. You guys all know how to find it in the sky. And this is how it looks to our eyes. The 3 bright stars are Orion's belt. The 4 stars are the corners. Right, Orion is what it would look like through an infrared telescope. And we can see the big clouds of gas and dust where stars are born. This is a very different view of the universe. And here's another good example. This is part of the Eagle Nebula, Pillars of Creation, as it's often called. And Hubble first captured it in 1995 in visible light on the left here. And it revealed never before seen details of these 3 giant pillars of gold gas bathed in the ultraviolet light from a cluster of young, massive stars. But in 2014, Hubble again observed this nebula, this time with one of its new cameras called the Wide Field Camera 3, which happened to come from Ball, actually. So this camera took images of the pillars in both visible and near infrared light. By using both types of light, astronomers can get a better picture of where and how stars are forming in the nebula. So what are Webb's goals specifically? So the first goal of Webb is to search for the first light after the Big Bang. This is the central overarching goal for the Webb mission as a whole. And our art here shows what happened after the Big Bang, the explosion that threw matter everywhere nearly 14 billion years ago. The universe was a very, very dark place after this. There were no stars, no galaxies. Then the universe began expanding, growing, what's depicted here. It took about 400 million years for stars and galaxies to appear. And scientists are still trying to figure out what happened after the Big Bang. They'll use Webb's infrared vision to peer back over 13.5 billion years to see the very first galaxies. And the second goal is to observe how stars and planetary systems form and evolve. So stars, as we know from previous presentations, are born and then they live and then they die. And we know that they're born in clouds of gas and dust, just like this photo. And some of the stars being born, you can see here. We know that this is happening, but we don't exactly know all the processes around how it happens. And we don't know why most stars form in groups or how planetary systems form. So Webb's infrared sensitivity will see into the furthest, faintest, oldest cosmic dust clouds where stars and planetary systems form. Oh, sorry, I didn't click ahead on that one. But goal 3, how do galaxies form and evolve? So Webb will look at how we ended up with the large variety of the galaxies we see today. We also know that huge black holes live at the center of most galaxies, but what is the relationship between the black holes and the galaxy that hosts them? We have a lot of questions about this, and so Webb will help with those. And then 4th, we want to study planetary systems and the origins of life, which has a special place in my heart. So the first planet outside our solar system was discovered in 1995. Since then, we've discovered thousands of planets around other stars. But most of the planets discovered so far are large gas giants like Jupiter. So our ultimate goal is to find a planet about the size of Earth and one that's orbiting just the right star, about the same size and heat as our star has. So it might have liquid water and perhaps even life. And using Webb, scientists will measure the physical, chemical, and atmospheric conditions of these newly discovered planets to see if life potentially exists on them. So this is the part that I've learned the most about this year, is engineering the actual complex. Because as you guys know, I studied astrophysics in undergrad, but now I'm moving more towards the engineering side of things. So how did we build Webb? So Ball's job was to design and build the telescope optics and all the parts that it needs to see. So we're in charge of all those little shiny mirrors that you've seen pictures of. And this photo is especially good because you can see our most prominent components. Of course, the huge primary mirror here, and then the secondary mirror, which is up here. And then like the nose-like structure that's protruding here is the AFT optics assembly is what it's called. There's, as you will find out, many, many acronyms in the aerospace industry that you have to get used to. But this structure contains the tertiary mirror and the fine steering mirror. But what you don't see here is the software controlling those mirrors, and we'll get to that in a minute. And here is an example of the light path from any star or object we're trying to observe would take in the telescope. So this is how the light will travel to the primary mirror, be reflected off the secondary mirror, as you see here, and then travel through the optics assembly where the tertiary and fine steering mirrors are located. And then the light will then be refracted or reflected and split and directed into the science instruments. Oops. Yep, that's correct. Sorry. All right. So here is just one segment of the 18 different hexagonal mirrors that compose the primary. It's coated with a thin layer of 24 karat gold because gold is highly reflective. It will then reflect most of the infrared light, hitting the big primary mirror into the second mirror. All of the mirrors combined are coated in a golf ball's worth of gold. And the mirrors are highly polished so that we can capture every single light photon possible. And the gold coating makes the mirror 98% reflective rather than 85% achieved by an ordinary mirror. But this is the fun part for me. So we're looking at the back of the primary mirror segment. And so each of Webb's mirrors, the metal has to be strong, lightweight, and hold its shape at the cold, cold temperatures in deep space. So we choose a metal called beryllium. And each segment started as a slab weighing about 250 kilograms or 550 pounds. And machinists at another company basically carved out the back of them according to our structural design that we gave them and brought each segment's weight down to about 46 pounds. And on the back of this mirror, most notable are the 7 actuators, 2 at each end of the hexapod and 1 in the center. So these are little devices. They're tiny mechanical motors that help move the mirrors into proper alignment with and curvature with each other. Our engineers had to actually invent the actuators that could move tiny amounts so small that the distance is actually measured in nanometers. But our actuators will move just 5 to 6 nanometers, and a nanometer is just one out of, it's a 10,000th the diameter of a human hair. So these actuators are actually what won Ball the contract way back in the day to work on Webb. So that means that each of these primary mirror segments has 7 degrees of freedom. So then the secondary, tertiary, and fine staring mirrors are also important. The round secondary mirror has 6 actuators on it, 6 degrees of freedom. And the third mirror and the fourth mirror, the fine staring mirror, which points the beam of light directly into the instruments. And then, of course, to Webb, we talked about this sunshade earlier. That's extremely important because nearly everything emits infrared radiation, including Webb itself. So we have to keep the science side as cold as possible to minimize its interference with itself. So it's only reading the infrared light emitted by the objects it's observing. And that's done in several ways, the most obvious being the sun shield. So this huge sun shield divides the telescope into a cold side and a hot side. The cold side, where the mirrors and the science instruments are located, is about negative 388 degrees Fahrenheit. The hot side, the sun side, will be about 185 degrees Fahrenheit. Nearly 600 degrees difference between the two sides, just separated by these tiny little things that look like sheets of aluminum foil. So these temperature extremes were a huge challenge for us in many ways. So most of Ball's electronic boxes are located behind each mirror, on the cold side, in other words. So we had to design cryogenic electronics, ones that would work in the frigid cold. But one of our electronic boxes is actually located on the warm side of Webb down here, inside the spacecraft bus. That means wiring had to run up from that box to the mirror's 132 actuators. James Webb carries 4 instruments in the module outlined in green here. Those instruments themselves generate heat, which somehow has to be removed. So Ball designed and built 3 cryogenic radiators that help remove the heat, and they're in the module's exterior. Oop. And so a little bit more about these science instruments. If we could look inside the module, we'd see the 4 instruments, and they're all housed in a metal frame. And those will receive the light collected by the telescope and use cameras, spectrographs, and coronagraphs to gather the science data, which are all things that I won't get into specifically here. But each instrument is designed to study a wide range of science objects and phenomena. So MIRI down here is what observes longer wavelength mid-infrared light. And the other 3 instruments, NIRCam, NIRSpec, and FGS or NIRIS, observe visible red to near infrared light. So that's going to be on the lower end of the spectrum. So because Webb is an international program, some of the instruments come from the European Space Agency, and one even comes from the Canadian Space Agency. And of course, once something is built, we have to test and test and test again, which is part of the reason we have not seen it launch according to schedule. I was at my NASA Goddard internship, and John Mather, the project scientist I mentioned earlier, came in and was like, yep, guys, we shook Webb. This was in 2018. We shook it and some things fell off. So we're back to we're back to putting those things back on and testing it again. And luckily right now it's gotten past all those tests. So how do we test the software? So Ball built a really cool 1/6 scale model of the James Webb Space Telescope called the Testbed Telescope, or TBT. So the TBT was used as a proof of concept for the commissioning flow that would achieve the required performance of the telescope. And commissioning work is ongoing. So right now, my team and what I do is run simulated software runs created by our Ball engineers to provide insight into the software improvements and creation of additional analysis tools. for the use of aligning the mirrors. And we're also developing a bunch of contingency plans. So in case something happens that we don't plan for, we are always going to be prepared. And we might even use the testbed telescope to test some of these issues if we run into them during the actual alignment process. All right, so this is a cool video. This is how they test the mirrors. They just shake the heck out of them. So with spacecraft, a lot of what we do is called environmental testing. We simulate the environments of launch and space. Vibration testing checked the mirrors to make sure they'll survive the extreme vibrations that occur during the launch. So the first 10 minutes are always going to be the worst. We literally shook each mirror on a vibe to make sure they could handle that stress. And just for reference, this is about 15 Gs in this particular test that those mirrors underwent. So testing also happened in extreme cold. So things don't work in space the same way that they work on Earth. So we have to recreate that environment. And that's what we did. We had a huge thermal vacuum chamber. And this is at NASA Marshall Space Flight Center in Alabama. And we can see 6 of the mirrors. And this is a Ball engineer actually helping to prepare the mirrors for testing. And to test that, we brought the temperature down to almost -400 degrees Fahrenheit. And we had to make sure the mirrors wouldn't warp, and they passed. Next, this is a fast motion movie of people at Ball working on Webb. So this is a mirror going through vibration testing again. And at the end here, you'll see people pushing the shipping cases that held the mirrors. So they all have to wear these bunny suits to make sure absolutely no dust gets on them. And then it was shipped out to Goddard, where during one of my other NASA internships, I was actually able to see it. We were preparing for a visit from the King of Sweden to come to a NASA center when I worked at the international relations part of NASA. And it actually shipped out 2 weeks before he came. But I got to go and do the rehearsal right when it was still there. And I have a really cool sneaky picture from the clean room of it. So now we're going to follow the mirrors to Goddard, the world's largest clean room. So this clean room is really cool. If you ever find your way to Greenbelt, Maryland, right outside of DC, I highly recommend you go check out whatever they're building in there. So the Webb telescope was mounted upright after a center of curvature test was conducted here. So these mirrors aren't actually completely flat. They'll have a slight curve, like a little bowl up to them. And the initial center of curvature test ensured the mirror's accuracy, and the test was repeated later to verify those same properties after the structure passed launch environment testing. Then more testing, you get the theme here. We tested the entire optical system. So the next year, the science instruments and the entire optical system was taken to NASA Johnson down in Houston to be tested in Chamber A, the largest vacuum chamber in the world. It was just an update from the Apollo days, actually, where they did testing there for Apollo. And to recreate the airless, frigid environment of space, it took about 10 days to pull the air from the chamber, and then about 1 month to lower the temperatures to the temperatures needed for testing. And then about 100 days of crowd testing later, engineers posed with the telescope after it merged from the chamber, which is hanging in our mission operations room, this picture. So this is in 2017. And the very final integration and testing, this is the progress of the last 4 years. So imagine it's gone halfway across the country. It's gone to Maryland, down to Texas. Now it's out Northrop Grumman, and now it's all the way actually in French Guiana, but we'll get to that in a minute. So this Northrop Grumman out in quite around the just around the LA area in California. So the optical elements and science instruments were shipped to Northrop in 2018, and they're the primary contractor for Webb. So what NASA does is they hold a competition for different aspects of telescope development. Northrop won the prime, and we are a subcontractor to Northrop. So they hire us to build parts of Webb. And so here it is being lifted out of its shipping container. And here it was mated with its sun shield and spacecraft bus, and the final testing was done. So we've mostly looked at the primary mirror. Let's take a quick look at the secondary mirror and its testing. So this was in 2019. In 2019, the engineers and techs at Northrop fully assembled the 2 halves of the telescope, the optical system and the instruments in the sun shield with the spacecraft bus. You'll see that in this time-lapse video. So this is really cool to see it actually like in process in the clean room. I can't imagine how scary that must be to have a $10 billion piece of machinery and carefully lift it up on these huge cranes that can handle so much weight. And then carefully slide it into place like this. And you see these silver pieces right here. That's actually how, not these silver pieces, these little poles up that you saw before. That's actually how the secondary mirror comes out. So this is it fully deployed without the secondary mirror. The secondary mirror is still folded in there, but it would come out and be in front of that nose cone in reality. So the final test for launch, technicians completed the final system testing over 17 different days in March 2021. They powered on Webb's electrical components and cycled through their planned operations to ensure each was functioning and communicating with each other. And they also checked that the instruments can send and receive data properly through the same network that they will use in space. Fun fact, I was actually the one who pressed go for the last mirror move in North America for this testing, which was very, very cool. And preparing to ship, in August, engineers finished Webb's comprehensive testing at Northrop and prepared to ship out to launch. And I won't play that video, but here is it in a French cargo ship that carried it to Kourou, French Guiana, which is in northeastern South America, and right along the equator conveniently. And so here we take advantage of Earth's spin to give the rocket an additional push at the equator. And at this time of the presentation, we are 39 days from launch. So what will launch look like? It's going to be launched by the European Space Agency because that is who owns that particular launch pad. So left here is the heavy lift rocket being used. This is called the Ariane 5. On the right here, you can see Webb stored in the rocket fairing. So it's all folded up. And as you can tell, the telescope barely fits within the 16-foot diameter payload fairing, which is the nose cone here. And the fairing's height is 56 feet. And so even that is a tight squeeze for Webb. And what will launch look like? This is not super important. It's just a quick video of the Ariane 5 actually getting prepared for takeoff here. And this is the exact same rocket that Webb will be launched in very shortly. I have not seen a rocket launch in person yet, and only a few people are allowed to go to French Guiana because there are so few hotel rooms actually that it's actually a struggle for people to go there for press and science purposes for this launch. Fairing separation. So Webb will have a 26-minute ride aboard the rocket, and then the telescope will separate from the rocket, which will trigger the solar array to automatically deploy. And it will start making electricity from sunshine and stop draining its battery. We like to call Webb an origami space telescope because this is how it's all folded up and then becomes deployed. So it will take about 2 weeks to fully unfold and then 2 more weeks to travel to its final destination. So it takes 4 weeks total to get there. But during that travel, it will undergo this process to get fully set up for science. And I'm going to let this play just because I think it's really interesting to see how the mirrors unfold. So you'll see the wings deploy here. One of our contingency scenarios is actually what happens if one of these mirrors doesn't fold out correctly? How do we still align the telescope? That would be a horrible, horrible scenario. And we'd have to explain to Congress why we spent so much money for it to not work, but let's pray that doesn't happen. So Webb will be very far away. It takes about 30 days for Webb to reach its final destination point, but it will take less than a day to get far away from Earth and much of the way there. So whereas Hubble is close to Earth, orbiting about 350 miles above us, like I mentioned earlier, Webb will be 1 million miles away from us. And so it's placed at a great distance to help keep Webb cold. And even though the sun shield blocks the sun, the Earth and the moon do reflect some radiation that could reach Webb. And so it will be at a point called Lagrange 2. And so this is where the fancy physics comes in. There are actually 5 of these so-called, quote, Lagrange points. And these are positions in space where the gravity of a two-body system like the sun and the earth can keep the telescope in its correct orbit. So that will allow it to use the least amount of fuel. It's kind of like a parking spot in space. And when Webb is orbiting the L2 point in the Earth-Sun system, it will follow the Earth around the sun, always in a straight line with the Earth and the sun. So as the Earth moves, Webb will follow, but it will always point away from the sun. And I'm almost done here. This is my favorite part because this is what I'm going to be doing for the next 6 months. So during the trip to L2, Webb will be fully deployed. It will cool down to its orbiting temperature and its systems will be checked and adjusted. And the Mission Operations Center can actually control each step from the ground. And it's based at the Space Telescope Science Institute in Baltimore. And this is a very hairy, nail-biting process. So these are some of the procedures that will continue 6 months after launch, after which routine science will occur. So 40 days after launch, once the primary mirror segments have unfolded and cooled down, we'll start using the wavefront and sensing control system to align those segments. So look at these very tiny little details of the segments actually moving here. So this is my role on the team. The alignment is needed to focus the light from distant objects. And during this process, engineers point Webb at a bright star and take 18 out of focus images of that star, one from each mirror segment. Then they use computer algorithms to determine how much they must move the mirror segments to align them. And the actuators will move the tiny, tiny steps needed to do that. And alignment will take several months to complete. And once Webb makes observations, its mirrors will be checked every few days to ensure that they remain aligned. And you can't see it right here, but I have a huge diagram. Maybe I'll lift up my computer and show you in a minute of just the complicated process that this commissioning is. So how do we communicate with Webb? Commands from Space Telescope Science Institute in Baltimore travel through the Deep Space Network, which is an international array of giant radio antennas that NASA uses to communicate with many different spacecraft. The Deep Space Network will then transmit the commands to Webb, and vice versa also happens. Webb will send us its images and data through the DSN, Deep Space Network, to Space Telescope Science Institute, where the data will be processed, distributed to the scientific community, and then archived. And anyone in the world can submit a proposal to observe for certain objects, and then a committee of astronomers will select the projects for the next year. The researchers have 1 year of private access to these new observations, and after that, the data become publicly available for download. So that gives astronomers a chance for people who have specific ideas to process the data and write up their papers before other people can as well. And this is crazy, but the nominal mission lifetime is 5 years with an extended goal of 10 years. So we spent 25 years developing the ideas for and building this telescope for it to hopefully last 10 years, which is crazy, but it's worth it. So the James Webb Space Telescope will be the world's premier space science observatory. It'll solve the mysteries of our solar system and make discoveries we can't even predict. And I'm proud to have a role in this mission and proud of our work at Ball. And I can't wait to see what we learned from Webb. So looking forward to launch, and let me know if you guys have any questions.
Very interesting. So does anybody have any questions for Katie?
When was the launch date?
December 18th, and that'll be at 7:20 Eastern time. So 6:20 a.m. Central time. And I'm sure you can see it on NASA TV and stuff like that.
How many light seconds away is the Lagrange point?
Ooh, light seconds? Good question. I think it's about a minute away. It's 1 million miles. So,
Oh, okay.
so if it's a million miles, it's about
93 million is about 8.5 minutes.
yeah. So something under a minute, just under a minute, something like that.
Aha.
Yeah, so it does take some time. Actually, most of our job on shift is we do all the physics analysis behind how do the mirrors need to move to make sure that we get a coherent light source among these 18 different segments. it's a lot of waiting for the data to come back down once we do the mirror alignment. So yeah.
Any other questions? Okay, yeah.
Ally has one.
Katie, I have a question. I have read that because at that L2 point, it's somewhat shaded by the earth, and there may be difficulties having enough sunshine there to fully operate the solar panel. Is it true that it's not quite at that point, so there's enough light to operate it? You know anything like
Yeah, so there will definitely be enough light to operate it with. It doesn't have, so it has solar panels to help get it there, but the main issue is getting it cold enough. So we have enough fuel on board, and each actuator has we have enough fuel for its nominal lifetime. Each actuator also has a limited range of motion. So after the telescope is aligned, it will stay in that alignment for all of science. And then eventually we'll, every 6 months or so, we'll check it, make sure it stays aligned, make any adjustments that are needed, and then continue on from there. But as far as like enough fuel for pointing, all it needs to do is be able to point to different places in the sky, which it has enough for its mission. So I'm not sure. So Allie, you had a question I just saw in the chat?
I did, yes. So with Webb and for the Big Bang, I think it is, the one I heard about in your presentation, was wondering about, okay, then where does Webb go to, I saw this a picture in your presentation between that and I'm sorry, I try and think of it. To the Big Bang. So where does Webb go after that? Is what I'm asking.
So Webb will actually, here, let me see if I can go back to the Big Bang picture. Maybe you were talking about, I think you might be talking about this one, but anyway, so Webb stays at the very same point in space. Oh gosh, I did not mean to do that. Anyway, Webb stays at the very same point in space the entire time. When we call it a time machine, it just means that we're looking at the light that's very far away. So it'll just stay near the Earth, but at that like orbiting point. And so Webb won't move, but hopefully it'll see things that are really far away. I hope that answers your question.
Yeah, it's kind of it's Webb, and what I saw in your picture in your presentation was Webb and the Big Bang picture.
Oh, yes. Yeah. So that was just a visual to help you see just how far back in time, quote unquote, or far away objects it will see. So that was probably not the best visual for like where it will actually be. Just picture like the sun, then the Earth, then the moon, and then Webb will be like way, way out beyond the moon, but it'll always stay right around the Earth and the moon. So it won't be like anywhere outside of that range. It'll just look at really far away things, which is cool.
So it kind of goes there, and so saying it does not move, or does it move? Well,
It just so it stays in line with the Earth.
oh, it
basically.
does.
So
Okay.
where the Earth moves, it moves, but it'll just orbit the sun with the Earth, but it
Okay.
won't go anywhere else.
Good, thank you.
Yeah, good question. Yeah.
My understanding is that it won't be exactly at the L2 point, but will orbit the L2 point.
Yep, absolutely. Yep, you got it. That's that professor talking there. Yep. It's just orbiting that point continuously.
Kate,
Yeah.
Katie, this is Ron. You had talked about the actual visual and the light that Webb is going to see, and really it's going to be only in the in the red range and the near infrared. So
Yes.
we're so used to seeing the beautiful pictures from Hubble, and we will not be seeing anything like that, correct?
I think we'll see different things. So you remember that picture of the pillars of creation that I showed? So on the left, there was that one where you could see the pillars and of dust and gas. So you could see just the dust. And then on the other side, it was in the near infrared. And so that's definitely in Webb spectrum. And we'll be able to see stars through that dust. So it'll just give us a slightly different picture of things. They're just slightly different objects, if that makes sense, or same objects, slightly different view of those objects.
Right. And we'll see the heated gas and dust and so forth because of the infrared that they give off.
Yeah. So if you saw the picture of Orion too, that's in a different wavelength even of infrared. So depending on what we want to look at, we'll be able to see different views even within the infrared spectrum itself.
Great, thank you.
Yeah, of course.
I think Mary had a question.
Oh, yep. I see that in the chat too, Mary and Mark.
How large is the battery, like diameter wise?
Good question. I would have to get back to you on that because I actually don't know. I was not involved as much in the building process. A lot of my coworkers were. And this is an example of where the energy source is. So I cannot give you, well, let's see. The mirror is 6 meters in diameter. Sorry. 6 meters in diameter. If I don't drop the $10 billion telescope, 6 meters in diameter. And then this is, I don't know, about 2/3 of that size. So I would say something around 4 meters is the back of this, which is where the energy source is. So that's the best estimate I can give you, but I will double check. And if that's wrong, I will let you know.
Okay, thank you.
Yeah. Let's see.
I'm wondering what happens if something does go wrong, or what do you do then? I mean, I know you don't want anything to go wrong or anything to
100%.
fail, but I suppose it could. So what happens then? I guess that's the reliability and engineering you coming through. How do you react to that?
Okay, this is a good question. So, okay, how do I start with this? Depends on what goes wrong. First of all, if launch and it blows up, we have a lot of explaining to do. Let's get it beyond Earth. Let's go to L2. Okay, so it's at L2, or it's at least deploying. So there's issues like, what if the sunshade doesn't deploy? That's pretty bad because we probably won't be able to do as much science because it won't get as cold. Okay, so let's talk more about the mirrors because that's what I know most about. There's different contingencies. So what if one of the wings doesn't deploy? So as you saw in the fairing, it's folded up. So actually only this main portion is out originally, and these three mirrors on the side are folded back. So a couple of our engineers are actually running simulations to say what happens when one of these doesn't deploy. And turns out we can still have a great telescope, but it just affects the resolution, like we described earlier. That the bigger the mirror, the better. And what if the secondary mirror doesn't deploy? That's bad. We definitely have a contingency plan for that, but I am not the subject matter expert in that. So we have about 32 different contingencies written up for all different scenarios. Like, what if we can't identify a segment on it? And what if we can't control a segment? What if an actuator fails? What if something is literally in front of the mirror that won't let us see the light as well? Yeah, so we have plans written up for all of that, and about 4 dozen people who will all sit in one room and yell at each other and try to figure out what's going to be best, probably at 3 a.m. And but yeah, we have plans written up for everything, and hopefully nothing we won't plan for.
Well, yeah, it sounds like there's opportunities for you to still use the telescope. It just may not operate as well, or may not be as functional in a lot of those cases. So that's
yep, absolutely. And one of the things that I mentioned is the actuators on the back that give it that range of degree of freedom. They have limited lifetimes. So we might get to the end and we only align it for one of the science instruments, one of the 4. And at the end, we have to make a big decision. Okay, do we mess everything up and re-average the alignment to make it benefit all of the science instruments? Or do we just leave it aligned for that one? Because we'll still get a good telescope for all the science instruments, even if it's aligned to just that one. The question is, do we want to mess it up and risk running out of actuators for further adjustments in the future, or not? So at some point, about 4 months into the commissioning process, we're going to have a huge meeting where we have to justify our decision for one way or another. And actually, I'm flying out to Baltimore to practice that decision tomorrow. So we'll see how it goes.
Okay.
I have to
Well,
present to
I
all the.
appreciate your presentation because you did answer a lot of the questions I had during the presentation. So thank you.
Oh, good. Yeah. And if you have any more, just email me. I'm always around. So I also saw Michael Henry on, and I wasn't sure I understand your question. I don't know if you're on still.
I guess the question is there propulsion in different sizes? Or is it just the same actuator jets to do everything?
Really good question. Dang, I should have brought my 3D. I have a 3D printed version of the actuator. And so, yeah, so there's actually fine range and coarse range on the actuator. So, excuse me, if we need to do a big move, like on the order of 1,000 microns, which is still pretty small, but it's a big move for us, we'd use the coarse range. And then if not, if we're just trying to do very fine alignment, we'll use the fine range, which gets down to that nanometer precision rather than the micrometer precision. So there's different ranges. It uses the same power source though, and it does use up part of the actuator's life. Like it has a limited amount that it can move over its cumulative movements. But yeah, there's different ways.
Is parking a big budget on the actuator? Does it take a lot of energy to park when it
Good
finally
question.
reaches?
Not that I know of, actually. The locking mechanism, I don't think it does take a lot of energy to do. No. That's a good question. I'll ask someone who is more expert on the actuators. I'm in on the physics side of things. So I say, here's what we should do with the actuators. And then there's another half of our team that says, we can't do that with the actuators, or this violates a workspace boundary and we'll run in, the mirrors will hit each other if we do that. So we can't do that. Whereas we're just saying, from the physics standpoint, this is what we would like to do. So I'll ask one of our actuator team members and make sure, because I've never thought about the parking and like the actual energy that takes. But yeah, good question. Sorry. I'll let you know.
Let's see, I think we had a question from Robert.
Yeah. Hi, Robert Mitchell. I was wondering, do they expect that the James Webb Telescope will be able to see far enough back in time to detect the light from the very first stars?
Absolutely. Yeah, that's one of the main goals of it, actually. So, yeah, it's kind of interesting. We've talked about it, right? So like when we are doing the alignment process, the goal is to look at one bright star on a completely black, well, it won't be completely black, but a star that's brighter significantly than all the other objects around it. And we expect, because these mirrors will move around so much on launch, that we'll see 18 different spots. Say we just had one target on a black space, we'd see 18 different spots from 18 different mirrors. But we've actually discussed the possibility that there is such high resolution on this thing that we don't actually see what we expect to see, because we see so much more. So that's an actually really interesting thing that could happen. But yeah, that's the point, is hopefully to see some of the earliest stars in the universe.
Wait, are you talking about enough resolution they might be able to resolve the actual photospheres of some stars?
Oh, potentially, yeah. So we're hoping to do that with exoplanet atmospheres, actually, is hopefully being able to see some of the spectra from those. But I'm not sure about like photospheres of like the most far away stars. Probably not, just, actually just observing their light.
More nearby ones, maybe?
Probably, yeah. Yeah, we'll be able to actually see maybe some more detail on the nearby stars, but I'm not sure what people have proposed to observe, so we'll see.
Star spots, maybe?
Oh, I think so, but we'll see.
So I have a question. Will you be able to actually image planets in nearby star systems?
Sorry, what did you say?
Will you be able to actually image planets in nearby star systems?
If you're talking about directly imaging, I don't think we have a coronagraph. Wait, we do have a coronagraph. So yes. Hang on. I'm not sure which method we would be using for it. Like, because there's like 5 different exoplanet discovery methods. I believe, yes, we would be able to, because there's actually an instrument with a coronagraph on it. So yes, direct imaging of exoplanets will be something that Webb does. But actually, more likely, more useful for that would be Webb, W1st, which is the other 2010 decadal. When I say decadal survey, I mean like what astronomers across the country said, hey, we really want this type of science done, and then let's build a telescope to do that. And so that's what W1st, or now called Roman, will be doing mostly. So we're going to be looking at atmospheres of exoplanets with Webb more than like exoplanet detection, if that makes sense. So.
Any other questions? Yeah, we got, Ann has a question.
Where did you get that beautiful necklace?
I got it on Etsy. I can send everyone the link if you're interested. There's also an awesome company called Startorialist that sells a bunch of space gear, and of course they're gearing up for launch. So I'll send Professor Al some links, and he can send out some links to the whole group of different space swag, because that is very important. So
Perfect. Very appropriate.
thank you. I've got my branded sweater on too.
Oh, yeah.
We're getting lots of little gear here.
Way to go.
For what it's worth, I've got an absolutely nerdish comment, and
Go
that
for
is
it.
the radius of the primary mirror, 3 meters. It happens to be the length of the largest recorder in the world, the subcontra base recorder in B flat. It's 10 meters tall.
Oh
Or sorry,
God.
it's 3 meters tall, 10 feet.
I didn't know that. That's so cool. I knew that there was a contrabass clarinet, but I did not know that there was a contrabass recorder. But that makes sense.
Yeah. And you know, to get the low frequency, it takes 3 meters of tube to do that.
Very cool. Do you have one? I'm assuming they're very expensive.
No, actually, they're more expensive than some cars.
Woo!
Well, there's only a few of them that exist in the world. They're made by one particular recorder builder in the Netherlands. Her name is Adriana Broikink.
Wow.
And if you're curious, I guess I could maybe look up a website and put it in the chat or something like that.
Yeah, send me a link. I'm always excited.
Okay, I need your address, or I'll just send it to Al, have him forward it. Okay.
Definitely send this link.
My boyfriend is
absolutely
now-
want to see this very long recorder.
He couldn't resist. He was sitting
Yeah.
on the
Okay.
couch.
Yeah. Actually, I own several. I own 2 different designs of recorders by Adriana Broikink. And this subcontrabass, it's a different design.
I'm gonna put my email in the chat for anybody who has any
Oh,
questions.
great.
So yeah, but I don't want to monopolize the whole rest of your evening. So I don't know if there's any final questions. Otherwise, feel free to email me, and I'm always around to answer stuff or answer things about going from astronomy to engineering too. Because I know that some of you guys are, in high school now, and it's really exciting. But as someone who just made the transition from astronomy to engineering, it definitely can be done, but it's kind of tricky. So always happy to help.
I have a quick question.
Yeah, it's always good to see you.
Anyway, compare where Hubble telescope is and where the new Webb is going to be. How many miles? Could I explain this to somebody's that? Not
Yes.
astronomy? How many
Yeah,
miles?
so that's a good question. So Hubble orbits Earth at 350 kilometers. So it's about 350 kilometers above us. And now compare that to Webb, which I know I'm going to use miles now, but it's about, Webb will be 1 million miles away. So it'll be beyond the moon is where Webb is going to be. So Webb will orbit the sun at the same speed as the Earth, whereas Hubble orbits the Earth every 90 minutes. So that gives you a sense. So 1 million miles away versus 350 kilometers away.
Thank you very much.
Yeah.
So I have to explain that to others that are not really into astronomy.
Yeah, that's why I love our club so much, is that we kind of help bring astronomy to everyone. And that's such a cool thing. So
Thank you. Your talk was very interesting.
thank you.
Well, thank you very much, Katie. This was really an interesting talk, and I know everybody's been holding their breath, hoping that everything goes well for the launch. And we've waited for it for a long time. I can't wait to see some of the images come back from it and the science that they bring forth, from the data that is collected. So let's hope for the best and hope the best for you in your future. And thank you very much for an interesting talk tonight. If anybody has questions, Katie's email note is in the chat. Or if you have, questions that you want to filter through me, that's fine. We can communicate that way too. But maybe if there aren't any further comments or questions, I guess I'd like to say thank you and maybe ask for a round of applause.
Thanks, guys. I love this club so much. So it's always fun to be coming back. So anyway, I'll let you get on with the rest of your evening.
Yeah, and you're welcome to stay on there. And we do have a few more things to do here. Let me see here. I'll go back to my screen. See if I can take, yeah, there we go. It's Katie's picture. So upcoming events. Actually, I guess maybe before I do this, maybe what I'll do here is I'll leave that picture up there just for the moment, but I'm going to stop sharing. One of the things that I'd like to do here is just say a word about awards. At our club banquet that we had last month, we had some award recipients, and I'm just trying to get caught up with those here. We have a member here by the name of Paul Levesque, and maybe Paul, if you could go up by the camera there. On too. Yeah, the camera's right up here. And
You're in.
you're in there. What I'd like to do is acknowledge your participation. This is a outreach award. This is from the Astronomical League. And we keep track of people's involvement in public outreach events. And if you have done 5 or more outreach events, then you earn an award. I don't know if can everybody see that? Or is it too small? Might be too small. And also there is a pin that goes with that. And I'll give that to you, and thank you very much. Congratulate you. Actually, there are, I think, I've kind of lost count, but I think there's 40 people in our club that have received that same award. So I think you're like the 40th person, maybe the 42nd person, something like that. I'll have to double check that. But thank you very much. Paul, and I think there might be a few more people that are close to having achieved that award. If not this year, we'll get them next year. Because this is for public outreach events. So observing sessions like we do at Niagara Zoo or at John Deere Middle School and things like that qualify. So let me go back here and go back to this. So upcoming events, I think everybody is probably aware there's going to be a lunar eclipse November 19th. And we aren't planning to, as far as I know, we're not planning to have a club observing session for this because it is actually the greatest eclipse occurs at like 3 a.m. in the morning on November 19th. But I just wanted to call that to your attention. It's not going to be a total eclipse. It's going to be about 97% or 98%. So it's almost a total eclipse of the moon. And I think it would be well worth the opportunity. There's going to be another one, I think, in, when is it, April? I think there's another eclipse in April, which will be a total eclipse. But as you know, the weather around here is pretty iffy in November and April. So if there's an opportunity, if it's clear, I'd say take your chances and look at it. If you've never seen a near total or total eclipse of the moon, it can be very interesting. You never know what they're going to look like. Sometimes they're very, very red. Sometimes they're not. It depends what's going on in the Earth's atmosphere. The reddish color is caused by light refracting through the Earth's atmosphere from the sun. So when we say total eclipse, it's not totally dark. You can actually see a little bit there from the light refracted around the Earth's atmosphere. So it's kind of a copper color or red color or blood moon, they call it. If you've ever heard of blood moon, that's a total eclipse. So let's see here. Let me see if I can get my computer page off here. Somebody's got a question about penumbra and umbra. There's a diagram of what it looks like. This is a primitive diagram I made. If the moon actually goes into the umbra part, that's the total dark area behind the Earth shielded from the sunlight. If it's in the penumbra area, then the Earth is only partially eclipsing the sun. So next meeting events that we have, November 17th. We plan to have an observing session at John Deere Middle School. And that'll be from 5 o'clock, and it'll probably be over at 7 o'clock. It's not going to go very late. Of course, sunset occurs very early now. And Dale, Roy, and Wayland are planning to attend, and I think Dino may be able to attend as well. I talked to him about it. He said maybe he could too. So if we have 4 people there, that should be good. November, and also if it's cloudy or rainy on the 17th, we have the 18th as a backup rain. November 20th is Niagara Zoo, and that's the last session that we're going to have at Niagara Zoo this year. Then we'll be closed down for the winter, and we'll put the PAC into winter storage. December 12th, we have tentatively a plan to put on a solar observing session at Clinton Children's Museum in Clinton, Iowa. We need to verify that. I haven't heard anything back from them in the past month or so concerning any details on that. So we'll have to see if that's going to go forward or not. But we might want to have a couple of scopes there for solar observing. And then the December 13th PAC meeting will be a business meeting. That'll be here again at 7 o'clock, December 13th, and we're going to have elections. Here's the elections that we have. This is the slate of candidates. The people that have either been nominated or nominated themselves are Dale Hatchell for president. Vice president is Dino Milani. Secretary is Paul West that we met earlier. Treasurer is Mike Haney. And observatory director is Rusty Case. And Roy Gustafson is Alcor. And Alcor, for people who don't know, that's our correspondent person that corresponds with the Astronomical League. The Popular Astronomy Club is a member of a larger organization called the Astronomical League that has about 20,000 members worldwide. Popular Astronomy Club was one of the first 10 organizations that came together and started the Astronomical League. And what year was it? 1946 or 47, something like that. So we're one of the founding clubs for the Astronomical League, and if you join our club, then you're automatically a member of the Astronomical League. And the award that Paul just received, that comes from the Astronomical League. And there's many other awards that can be gleaned from that. There's educational programs. There are scholarships for students. There's all kinds of things that you can get for your membership in the Astronomical League. So those are the people that are running for office. I've decided to step down as president. I've been president for 6 years, and I love it. I really don't want to quit, but I think it's been long enough, and I would like to allow some new leadership, some new ideas to come in. And I'm still going to be on the board. I'm not an elected member anymore as a past president, but Waylon is.
And I'm off the board.
Waylon is celebrating, I know. Waylon was my past president and really supported me, and his wife have been a great help to me, as well as my wife, Sarah. And it's been great. The club has really done well, and I'm just really happy to have been part of it. I want to thank everybody. Now, I just want to throw the slide up here and ask, the people that have their names on this slide, you better think long and hard about it, because once you're elected, then it's too late. So if you got any qualms about it, you better not. But all terms? 2 years. These are two-year terms. 2 years. So it's not a prison sentence for very long. And yeah, I mean, it's, this is supposed to be fun, and it is. It should be fun. This is a hobby. The Popular Astronomy Club is a great educational thing, and it's a social thing. There's been a lot of fun things that have happened. We've had conferences. Our North Central region, the Astronomical League conference. What a great thing that was that we hosted. Anyway, and then of course December is Christmas. Maybe somebody will get a telescope for Christmas.
Allie wants to know if we really have to put that.
What's that?
Oh, it's something in the sky, right?
Is there anything else that anybody wants to talk about? Yes.
Was there a Aurora Borealis on Saturday night?
That's a good question.
I don't know. Did anybody see any northern lights?
They predicted that. I know several people who looked, but I have not, I'm not aware of anybody who actually saw anything in this area.
Wake up, Byron.
Still suffering from the other night.
If we don't have anything else, I think we got a few minutes here. I do have some pictures to show. Yes.
I'll say one thing that we have passed the halfway point on membership renewals for the coming year. So if you have not renewed yet, now is the time to do it.
And I just want to bring up quickly that QCAS is having a public night at Menke Observatory on December 4th. Weather permitting, if anyone's interested.
And everybody's invited to that, right?
Yes, everyone's invited.
And Menke Observatory is a really nice place. It's north of the Quad Cities. It's about as dark a sky as you're going to find without driving too terribly far from the Quad Cities. And it's a nice observatory they've got there too.
Only about half an hour drive from here. It's at the Wapsie River Environmental Education Center, just outside Dixon, Iowa.
Now, let me see. I want to show some pictures here.
Thank you.
Need to figure out how to share my screen again.
Short memory.
Yeah. All right, let's see. Everybody see that?
Yep.
Byron, are you still awake?
Yeah. I was up until 4 o'clock after the fall back that night. That's why I'm real drowsy tonight. I'm still suffering from that, but yeah, that's NGC 891 in Andromeda.
Byron, you want to tell how you took these pictures, just real, roughly?
I had I fixed my Newtonian. I got the cat's eye system, realigned the optics, and took it down. I used the C-GEM this time. And a Canon T3i, just stock, unmodified. And between that and on-camera guiding with PHT 2 software, and just went at it for a long time.
So this is looks like a galaxy that we're looking at edge on, right?
That is correct.
That's neat.
Are these that list that I got from you?
Yeah, it's some of it's off that list. Here's the Pelican. That's IC 5070 Pelican Nebula.
Now the Pelican itself is what, right here?
Yeah.
It's kind of the dark nebula that you're seeing.
Yes.
I don't know if that's showing up on the screens.
Yeah, you can see it.
Yeah. That's really neat. And I really like the stars. Those spikes are cool.
Yeah, I like that too. There's your California Nebula. And I think that's NGC, I think it is 1499.
Nice. How long of a time exposure is this?
That one was probably at least 5 minutes. I was doing 5 to 6 minutes, and there's your rosette.
That's
trying
neat.
to think of that number.
NGC
22 something.
2237.
Okay.
I'm just reading your file.
Oh, okay.
Hopefully that's right. But
I try to put that in there so you guys can tell when you look at what it actually is. But yeah, that was the gem of the night there.
Yeah.
Between that and the horse head.
Yeah, can everybody see the horse head?
Mm-hmm.
Right here. I don't know if you can see my cursor?
Yeah.
Yeah. And then here's the flame nebula over here. That's really cool. And that star there is really bright. Wow.
Yeah, isn't it though? Look at the spikes on that thing. And there's your Pac-Man, which I've never photographed it before. So I thought, well, I'll see what I can pull out of it. And the skies were, I mean, even though it was dark down there, it was kind of hazy Saturday night.
NGC 281.
Okay. That sounds about right.
Wow. And those are the only ones I downloaded. I saw you had some others you sent me this short.
Yeah, I got the Crab Nebula I sent you, Iris. Here's, yeah, right there you go.
I didn't download it, but can you see that? I don't know if it. Yeah. That's really beautiful colors.
Yeah.
That's what
Yeah. The crystal ball from Taurus is in there too.
This is the crystal ball right here.
Yep.
NGC 1514. Nice.
Oh, there's the bubble.
Yeah.
NGC, well, what is that one? That's
635.
okay. Yeah.
Nice.
You see the bubble?
It looks like a soap
bubble.
bubble. It's a perfect circle, isn't it?
Yeah, if that spike would have came down lower, popped it. Here's your Iris. That's got a lot of dark nebula around it.
Yeah, you can see there's a lot of stars out here, but right around it, it's like shielded.
And this is the elephant trunk. It wasn't as good, but I mean, you can see some of that dark lane.
Which one is the elephant trunk? Is it over here?
You know,
or down here?
I don't know for sure. I did precision alignment on it. I mean, there's something right there on the bottom, and then right there on the very bottom. I don't know if that's what that is. I never really seen too detailed of a picture of it. Of course, there's also a dark area there off to the right. It kind of goes up through the screen. So I'm not 100% sure, but I'll have to revisit that one again.
There's a lot of stars out there, man. That's cool.
Yeah, it's right in the Milky Way. I tried the Heart Nebula. It's too big for the scope. That almost needs to be a camera shot on top of the telescope, a piggyback shot. And I tried the Sol Nebula too, and couldn't. I don't know. I'll have to, like say, revisit those. Because last time I was down there, my parents, it had just rained, and that atmosphere was nice and clear.
Those are really nice pictures.
Well, thank you.
I had a couple here. This was from the Doll Museum. When was that? Friday night?
Mm-hmm.
We had really nice, it was kind of hazy, but it seemed like the planets were just really, really beautiful for some reason. I don't know, there's something weird going on in the atmosphere, but there was a transit of Io. I think Io is right about where I'm pointing there on that drawing. It might be a little bit hard to see, but there's like a little white dot right there. It's really faint. But there's the eclipse shadow of it on the surface of Jupiter. That was really cool.
Nice.
That's a closer up view of it. And there's Saturn. Now, these pictures are actually stacked images of 60 seconds of video. And
You can see 2 divisions there.
yeah, you can definitely see 2, maybe 3 even. Looks like there might be one here, as well as one further out. I think the other picture I had, I didn't magnify it quite so much. It might be cool. It's kind of hard to tell. If you can spend, I can spend hours, processing these pictures, and I'm never satisfied. There's Venus. It's kind of a waning crescent now. It's really nice. It's going to get bigger and more of a smaller crescent while it approaches Earth now. So you're going to want to watch Venus. If you have a telescope, you can easily resolve it into a phase like this right now. It's really cool. Does anybody else have any pictures they want to show?
Speaking of pictures, are we ordering calendars this year? Isn't this the time of year we're usually ordering calendars for the next astronomy calendars?
Well, it hadn't even occurred to me. I don't know.
We should make one.
Yeah, you could make one.
Hey, wait a minute. I think that's a great idea. We probably could make calendars, couldn't we somehow? Does anybody have the ability to do that?
I can provide the pictures.
Yeah.
I know.
Wonderful. Shutterfly, you can make them, you can order from different photo places online. Okay.
Does somebody want to check into that? That would be really cool. We could make our own calendars. I don't know what they would cost. But I haven't even thought, to be honest, I haven't even thought about calendars. I mean, how many people are interested in calendars? What calendars are you talking about? Astronomy calendars?
Well, we normally get one from astronomy, I think it is, that we used to, I don't know, 10, 12 bucks.
It was at least 2 years ago, maybe 3 years ago. It was when I was first treasurer. We ordered them from astronomy, and they didn't arrive until about March.
Oh.
They had all kinds of problems with them.
Oh.
And I haven't even seen any advertisement from them since then. About
Yeah, I think
ordering
I went
calendars.
to Books A Million this last time to get one.
I think, well, I ordered one from, I think it was from Sky and Telescope, and I got it, like a month or two ago.
How much was it?
Oh, some nominal amount, a little over $10.
Would there be any savings? I mean, if the group ordered them,
I have no idea.
I think that's the way it used to be done.
It used to be that way, but I don't know.
Yeah, I don't know.
Group order.
It may not be because at that same time too, they changed the club subscription policy, and it was no cheaper to order through the club than it was to order direct.
Oh.
So, but I do not know for sure about that in regard to the calendars.
Okay.
Well,
When it
maybe
was
we
for
can,
the subscriptions.
then we can check on that. If there's no cost benefit to, ordering them, it would be much simpler, I think, for individuals just to go ahead and do it, and you wouldn't have to process.
Yeah, just look at the website.
Yeah.
Yeah.
But I'm intrigued by the idea of making our own calendars. Maybe we could think about doing that. If there's a time that's too short for next year, maybe we could take a look at what it would take to actually do that. We could get a blank calendar, add photography to it. Anybody else have anything to discuss? Any questions? Any observations?
I think I'm going to take off.
Okay,
See you all guys next month.
thanks, Jerry.
See you, Jerry.
And I guess if there isn't anything else, I'd say we're adjourned. Thank you very much, everyone, for attending, and thank you, Katie, if you're still on the line for.
Nope, she left.
Great.
Yep, she left.
Anyway, thank you to everyone.
Good night, all.
Bye, guys.
Evening,
See you later.
Have a good night.
Hey, Al,
Yeah,
after this recording, can I have a moment with you?
Yes, it is.
pardon
About
After this recording, can I have a moment with you?
No.
Oh, yeah, let me turn off the recording. Let's see.
Well, thank you, Mr. Johnson. I don't know that I will be joining you. but- And there's so much I don't know that it would take me just my life to. How do you know about the galaxies and where they're located? And how you got that mention, you mentioned so numbers.
You gonna be there on 17th?
Probably not. By the time I would get off my car and get off, drive all the way out there. My class is on Central 6, and by the time I can change and get out of there, usually I got parents to talk to. 'Cause I get all the kids and it's about, yeah, I get all the new kids.